So in this problem, we're gonna calculate the critical load at which the adapter of a rocket will buckle. And to illustrate this, we can first draw a picture of a rocket here. Alright, and here we have the nozzle, and the fire comes out here. And usually how rockets are built is that they have an adapter here, and on top of the adapter is usually the payload. So that's usually a satellite. And around that, of course, we have a nice fairing to make everything nice and aerodynamic. And what we're going to want to calculate is the load at which this adapter here will buckle. And to do that, we have to look up formulas. And there is a formula to calculate this. Basically, it gives you the critical buckling stress over the E modulus. And that is equal to, alright, this is going to be a little ugly, but this is what the formula looks like. T over R to the power of 1.6 plus 0.16 T over L and to the power of 1.3. Now, yeah, to derive this formula, that would probably take too long. So we're just gonna assume we have this formula, and let's also assume that we know the thickness of the adapter. The adapter, by the way, is will look like if we look for it will be a hollow cylinder. So if we look from the top, it will look something like this. So it will have a thickness, and in this case, that will be equal to 1.5 millimeters, so 0.0015 meters. Radius is equal to 0.2 meters, and the length of the adapter is equal to 0.8 meters. Now, you probably see already this is rather easy to do. So we basically plug in all the values here, and we can then multiply this part with E. So that'll give us critical buckling stress. Yeah, let's do this quickly. Times the E modulus. Oh yeah, the E modulus also given. That is 70 gigapascal. And now we also know that the stress is force over area. So what we basically have to do is that is the stress. So what we basically have to do to determine the critical buckling load is to multiply the critical buckling stress times the area of this whole cylinder. So we just have to multiply this, and that will give us FCR. So we plug in all the values in this formula, and we get a critical buckling stress of, what was it, 254 megapascal. And the critical buckling load, oh yeah, we have to also determine the area of this, but that's quite easy to do. We we can use the thin wall approximation for this, and that'll give us times 2 pi r times t, and plug this in, plug in the radius and the thickness, and that'll leave us with a critical buckling load of 477 kilonewtons. And that's it for today.